Thank you. Good morning. So this will kind of carry on that theme that we've heard from the two speakers so far today. So parallel computing, one of the first ones I ever used, actually the first parallel program I ever wrote was in Occam on a transputer in 1989. I can remember it well. But the year after that, I had some amazing new toys. This was at university in Cardiff. And we had an N-Cube. It was an amazing machine. This had 64 processors in it. And I was hooked. I've been writing parallel programs ever since. But really, parallel machines were very special back in the 80s and 90s. They kind of looked like this. They had flashing lights on. But today, as we all know, it's now everywhere. So this is an 8-core SoC that, in addition, has a highly parallel, highly programmable GPU from Imaginations, has ARM cores in it, and that's a consumer electronics device. So your mum might have an 8-core, highly heterogeneous, very, very fast device in her pocket. So it's just amazing how this has all become very mainstream in a short amount of time. Most of my work is in high-performance computing. I work on gigantic machines. This is the fastest and biggest in the world today that we know of. It's in China. It's a 33 petaflop supercomputer, has 16,000 nodes, so 16,000 separate machines all linked together. Each one of those nodes has 2 multi-core high-end CPUs and 3 many-core Intel Xeon Phi accelerators, all in each node. And all of that gives you over 3 million cores. 3 million cores. Imagine having that, writing one program to try and harness all of those. Of course, this is back in the realm of big things with flashing lights. That cost nearly $400 million, so there aren't too many of these around, and uses 17 megawatts, 24 megawatts if you throw in the cooling. So these are quite big, quite expensive machines to cool, but there are scientific problems that we just cannot tackle without some machines like this, and there are lots of scientists who can't do. It's like saying we're going to have no more powerful telescopes or no more high energy instruments to smash things and have a look at particles. So these are computational instruments these days for doing some amazing science. So I put a slide like this up here about 3 years ago, and I said at the time, it's amazing. We have a kind of re-proliferation of parallel programming languages. This was a sample that I knew people were actively using about 3 years ago. Now, what do you think has happened in the last 3 years? Have any of those gone away? No, that never happens, does it? We only ever get more, so more have come along. Some of these may not have kind of really taken off, but very few of them ever really go away. In fact, what tends to happen, we get more. So in fact, fairly recently, there have been a couple of developments. C++11, actually C++14 has just been ratified, has started to add a lot more to do with parallel programming in the base C++ standard. So I'm going to say a bit about that in a minute. But also there's this thing called Metal that's just come out. Anyone heard of Metal? This is something that's come from Apple, and it's very interesting. In fact, it really calls back to David's talk, which is everything's got too complicated, so we need to go back and kind of start again. And actually, Metal is Apple's let's go back and start again. All of those group into various categories. So we've got the partition global address space category. There's message passing, which is in high performance computing. That's still MPI. It'll just carry on being MPI for a while, it looks like. The GPU languages like OpenCL and CUDA, that's actually where Metal fits in. It's a new GPU programming language. And then we have C++11. Arguably could go almost anywhere in that set, but I've put it in the multi-threaded set. So some of these are targeting GPUs specifically. That makes sense. GPUs are highly parallel. They've become fully programmable. And because this has been a relatively recent thing, everyone's been wrestling with what's the best way of really targeting these devices. And also, as David said, the architectures have kept evolving. And that's made life hard for everyone. It's hard for the programmer. It's hard for people designing the parallel programming languages that are aiming at a very fast-moving target. So OpenCL, we've watched OpenCL itself, which is something I'm involved with as a standard. That's actually been evolving very rapidly. It started with version 1. We've had version 1.1, 1.2, 2.0, we're hard at work on 2.1, and that's all in a very short space of time. And the feature set has changed a lot in that short space of time because the architectures have been changing rapidly. And that just makes lots of work. It's very interesting, but it is a lot of work. Microsoft has their direct computers response, C++ AMP, etc. But some of the other things are also taking aim at these architectures. OpenMP as a standard. OpenMP4 now supports many core architectures, has a number of different models for doing that. It's already supported on the Intel Xeon Phi. It could be supported on current generation of GPUs if the work was done, etc. So it's very interesting to see what's been happening in this space. But Apple's Metal, this is very recent, just in the last few months. It's a very, very interesting evolution, so I thought it'd be worth having a look. It is a ground-up redesign, largely to get rid of all of the overhead and all of the legacy. So Apple, there's not many companies that could do this. Apple, maybe Google. I'm not even sure Samsung could try and do this right now, but because they control their entire ecosystem, they said, right, a lot of this works quite well, but over time we're using OpenGL and things like that. We've got loads of overhead, lots of things happening that we don't really want, so we'll just start from scratch. And we'll create our own standard, our own API, and because we know what the hardware is going to be, we know what the applications are going to be, we can do this. And they have. And it's really interesting to see what they've chosen to do. It's been designed targeting GPUs. It's designed to replace things like OpenGL and even things like OpenCL, OpenGL, interop. It is designed to be close to the metal. That's where the name comes from. And really it's about removing all the overheads. And a lot of kind of baggage has ended up in the whole kind of OpenCL, OpenGL software stack over time, because these things have been around for a while. They've accumulated lots of functionality, lots of features. Nothing ever gets thrown away. So you have to be able to do all of that old stuff you did 20 years ago and the new stuff today. So Apple said, right, let's start from scratch. Let's see what we can do. It's got a shading language based on C++11, and it does things like precompiling shaders and building them in. And the motivation for Apple is they know they have SoCs of their own that are highly parallel. This is the A7, A8's in the latest devices, but even the A7, you can't see it very well on this picture, but it has dual core CPUs. It's got a very programmable GPU and lots of other devices as well. They know they have this parallelism that they really want to exploit. And for them, this is not just about extracting all the performance from these multi-core systems. It's also about the efficiency and about the energy efficiency. So all of this bloat in the software stack is not just slowing it down, it's using up the battery. So that's why Apple was very keen to do this work. So what's it all about? Well, at the moment, Metal, it is a proprietary API that Apple's come up with, but they've done things like this before and then opened them up. So even OpenCL was actually an initial an Apple creation, and then they went to Kronos and said, we'd like to make this an open standard, can we do that? So Metal may become an open standard, who knows? They were targeting a fairly big improvement in performance. Their goal was 10x more draw calls per frame. That's a huge increase, And it meant really throwing away all the overhead that was in OpenGL and things like that. This is focused on iOS, at least for now, but who knows? Kind of watch this space. Maybe this will aim at their desktop stuff and MacBooks as well at some point. It's a really thin API, and it has to be. If it's going to be doing 10 times more draw calls per frame, it has to be really, really thin. Designed for all the latest GPU features, so that's things like shared memory with the CPU, full programmability, all the things that you might want that are in the GPU, targeting those. And the aim has been strip out everything you can, all the expensive CPU operations like runtime compilation for shaders. All of that has to go from runtime, has to go somewhere else, has to go into compile time or into content load time. They want to make performance more predictable. It's again something that David mentioned, and that's partly by in things like OpenGL, lots of the functionality ended up being owned by the drivers. So things would happen that were not under the programmer control at times that were not under the programmer control. So all of a sudden your frame rate might slow down and something was happening that you couldn't control. Apple's basically said, no, all of those things now will only happen when you say. So the programmer has a bit more work to do, but now you have kind of full visibility and therefore more predictability about when everything's going on. So this does look pretty interesting. There are 3 different types of commands. So you want to do some graphic stuff, you want to do some compute, and then there's some low-level kind of blitting of frames and things like that. And they're just 3 different kinds of commands that can all go into the same command queue. That's quite different from, at the moment, from a sort of OpenCL, OpenGL interop point of view, where you have different software stacks and you're switching mode between one and the other, and there's lots of state that has to get saved. Here, these are all just commands that go in a queue. So much lower overhead. That saves lots of saving and restoring, which saves time and energy. And they've even thought about how do we generate these commands. We know we're going to have a multi-core CPU, so we want to be able to generate commands from lots of different threads. And they thought about how to make that really scalable in a way that doesn't need atomic locks and all those things that are complicated and slow you down. So it's very, very neat. It's been designed for unified memory systems. In the past, maybe you would have had to have assumed you wouldn't have that. But Apple knows this is going to be an SoC. We're going to have CPUs and GPUs that are going to share memory. So that gives them some advantage in designing the API. It means you don't have to have these implicit memory copies. That's one big advantage. It means they've got some coherency going on that they know they can exploit. They don't need any explicit CPU cache management. That's good. Again, it does mean a bit more of this is in the hands of you as a programmer, but it means you should be able to design things that are simpler, more predictable, so it kind of fits in with Apple's overall mentality, what they've been trying to achieve here. What's the impact been? So this is what Kronos has done in reaction. Next generation OpenGL has been one of the big kind of outcomes of this. So it's great. In a way, Apple's really upset the apple cart. I'm really sorry about that. But it's really helped because what's happening is it's introduced some competition. All the other APIs and standards are going, we need to respond to this, otherwise we're dead. We're going to be gone. So there is no technical reason why something like OpenGL couldn't do something just like Metal, but in the past it's been very difficult. There have been a number of initiatives to try and make this happen, and it just didn't gather enough momentum. But now there's enough people saying we've got to respond, otherwise OpenGL will die. So there are some great projects underway now to try and do a Metal, but with OpenGL, a brand new OpenGL, clean sheet design, get rid of all of that overhead, and hopefully that will be possible. So fingers crossed this will actually come to fruition. So that was Metal. Now C++11's also been adding in lots of new features. So standard thread is now part of the standard C++ library. It's not optional X or anything like that. It's now got things like lambda expressions, which are a nice way of expressing parallelism. And there's lots of other things going on. If you look at the C++ website, loads of different groups looking at parallelism and concurrency in C++14 and beyond. So here's what lambda expressions look like. I know lots of you in the room have used things like this in the past. Well, now they're just in the base C++, which is great. Here's a simple stack speed program expressed in this form, really simple. So it'd be very interesting to see if this starts to become more widely adopted and if people start using C++ as their parallel programming language. There is more going on there. So we are currently around about here. So we've had C++11, 14 was just ratified a month or two back. And if you look at all the other things still going on, as we're marching towards the next major C++ release, which is in 2017, concurrency and parallelism, two of the major activities are all based on this issue. So it's going to be very interesting to see how much of all of this kind of stuff we've been talking about actually starts to appear in the mainstream programming language. The programming language has just become parallel. It's not a separate thing anymore. So watch this space. And hopefully some of the speakers later on will talk about this sort of issue a bit more. So we are still going through a renaissance. This isn't just for a niche. There are no serial systems anymore. Everything is a parallel system. There are no silver bullets. When you've been around for a while doing these kinds of things, you'll notice, hang on, that's just very like something I've seen before. And that's kind of no surprise these days. In high-performance computing, everything's multi-core, really going to many core very quickly. And in embedded systems, everything has gone heterogeneous as well. If you look at any SoC, pretty much, any phone or tablet or anything like that, they're all multi-core CPU and a programmable GPU. It's amazing how quickly that's happened. Standards like OpenCL and OpenGL, they are evolving, they are competing, and it's great to see Apple kind of stimulate this new spurt of innovation and creativity. And it's also great to see the main standards like C++ continuing to evolve to absorb some of the things, the fundamentals that we really need to do parallelism anywhere. So watch this space. Thank you very much.
Thank you very much. There's time for questions. There is a question.
My name is Mark Honman with Sundance Multiprocessor Technology. A question regarding languages, and that is the problem of conceptual simplicity, which is really the solution to the question that was asked of David May, the problem of the dumb programmers. And is there any hope of conceptual simplicity coming to the fore in languages? Because everything you've shared today seems to just be perpetuating the same conceptual design challenges that have existed for time, or since time immemorial.
That's a really good question. So I've seen little evidence that there is a magic bullet of here's something that's really nice and simple that anyone could do that also gives you high performance code and what you really want. It just seems to be that once we go into parallelism at all, or never mind anything that's heterogeneous or anything that's more complicated, we've never found the thing you would really like, which is something that is nice and simple that anyone could do that will also work well and give you good performance. Just don't seem to have it. And people have been looking for a long time, so maybe it just isn't possible. And it's very interesting to see Apple's response here, which is they could have gone either way, right? They could have gone, here's something that's really, really simple, so we have lots of app developers, or something that in a way is more complicated, but you get better performance. And Metal it's actually got more complicated, closer to the Metal, thinner API, more exposed. So it's very interesting to see that happen. Who knows? Maybe one day, but I wouldn't bet my mortgage on it.
Okay. Thanks, Simon. Thank you very much.
Thank you.